So we're going to talk about how the derivatives affect the shape of a graph. So we're going to now compare the original function to the first derivative and the second derivative. Okay, we've already done some of this. Hopefully you're going to say, I know how to do that already. And then there will be parts that are new. We're going to talk about concavity in here that I've quickly mentioned in class. Okay, the first thing, increasing, decreasing test, we already know this. If the derivative is what? Positive, then the original function must be increasing. If the derivative is negative, then the original is decreasing. We already know that. The first derivative test, again, we don't need to know it by name, but the first derivative test lets us find local max and mins. So that's what we're talking about here. Okay, so we already did global or absolute max and mins. Now we're talking about how do you find a local max or min? Okay, here's how. If the first derivative changes from positive to negative at a critical number, then you have a local max, which is pretty obvious. Okay, if the derivative was going from being positive to being negative, then the original had a local max. If the first derivative changes from, negative to positive, then I have a local minimum. Okay, so it's going to be at a critical number. Remember what a critical number is. Critical number is where the derivative is 0 or does not exist. Then you have to see if the derivative changes sign at that number. Okay, first problem. So find where I'm increasing, decreasing, and find the local min and max. So what am I going to do? I'm going to use the derivative. So I'm going to find the derivative of that function. F prime of x would equal 12x cubed minus 12x squared minus 24x. Okay, I'm going to set it equal to 0 and I'm going to solve. So divide everything by 12 and factor an x out. So if I divide everything by 12, take an x out, now I can solve. So factor this, minus 2 plus 1. So my critical numbers, which we just did, are 0, 2, and negative 1. Okay, those are my critical numbers. Now, if I want to know where I'm increasing, decreasing, what do we need? We need the first derivative sign chart or number line. So I know that at 0, at negative 1, and at 2, I'm 0. So now I'm just going to test. Now, where do you test? This is the big question. I'm testing in the first derivative. I want to know, is the first derivative positive or negative? So I'm going to plug negative 2 into the derivative. I'm going to plug it into the factored form. And this becomes negative. This in between here is positive. This is negative. This is positive. So you're plugging in like negative 2. And you're getting a negative. You're plugging in negative 1/2, and you're getting a positive. You're plugging 1 in, you're getting a negative, and you're plugging 3 in, and you're getting a positive into the derivative. So now, since the derivative is negative here, the original, so f of x, okay, must be what? It must be decreasing from negative infinity to negative 1 or 0 to 2. Because that's where the derivative is negative. And f of x must be increasing from negative 1 to 0 or 2 to infinity, because that's where the derivative is positive. We've already kind of done that before, guys. We've done it with velocity. You've figured out where velocity was positive, negative. Okay? Now, find the local minimum and maximum. I've already done all the work. Okay? Because this shows that the derivative went from negative to positive. So I have a local minimum at negative 1. Okay, I know that again because the derivative went from negative to positive. Okay, so negative 1 at negative 1 is a local minimum. So I have a minimum at negative 1. Now, how do you actually find the minimum value? You plug negative 1 into the original. So now I would go and I would plug negative 1 into my original function to figure out what the minimum value is. Okay, and you should get 0. So I have a local minimum of 0 at negative 1. I have another minimum at 2. So at 2, I have a local minimum, because again, I go from negative to positive. And if I plug 2 into the original, I get negative 27. So I have 2 local mins. And then you have a local max at 0. Okay, I'm just trying to squish this in. So I have a max at 0. Why? Because at 0, the derivative goes from positive to negative. So then I would plug 0 into the original, and I get 5. So I have a local maximum of 5, and I have 2 local minimums of 0 and negative 27. Okay? Same exact problem now with a trig function. So if you want, you could stop it, and you could try this. So you're going to do the same exact thing. You're going to find the first derivative. You're going to find your critical numbers. So g prime 1 plus 2 cosine of x. Derivative sign is positive cosine, not negative. I'm going to set this equal to 0, and I'm going to get that cosine of x equals negative 1/2. Hopefully we know when this equals negative 1/2 on the interval 0 to 2 pi. I get 2 pi over 3 and 4 pi over 3. Okay, so those are your critical numbers. That's where the derivative is 0. So now go to my number line or my sign chart. Sign chart, it's just showing the signs, positive, negative. Okay, so I have 0, I have 2 pi over 3, I have 4 pi over 3, and I'm going to just test my regions. Okay, so I'm going to test between 0 and 2 pi over 3. So I could test pi over 2 to figure out that region. Again, where are you testing in the derivative? You want to know if the derivative is positive or negative. So I would plug like pi over 2 into this, and I should get a positive. Then I would check between 2 pi over 3 and 4 pi over 3, which I could check pi, get a negative if I plug pi in. Okay, and then I could check over here like 3 pi over 2, and I get a positive. So what did we just find? We know that I have a local max at 2 pi over 3. So local max at 2 pi over 3. Why? Because f prime goes from positive to negative. Okay? I have a local minimum at 4 pi over 3. Why? Because the derivative goes from negative to positive. Now, what's the actual value? Now I would plug these in to the original, because I'm trying to find the max and min of the original. So I'd plug 2 pi over 3 into the first one, and I'd plug 4 pi over 3 into it to get the actual values. So I would get 2 pi over 3 plus root 3 as my max, and 4 pi over 3 minus root 3 as my min. Okay? Next one, I just had the same exact directions. Now I just have it with a rational. So go ahead. Again, you could find the derivative of this. We should be able to pretty quickly. Okay, I'd use quotient rule. Derivative of numerator is 2x times denominator, x squared plus 4, minus numerator, times derivative of denominator, 2x, all over x squared plus 4 squared. There's my derivative. I want to simplify it a little bit, so I'm going to pull out a 2x. Okay, right away, that would be the easiest thing to do is factor something out. And I'm left with x squared plus 4 minus x squared plus 4 all over my denominator. I simplify that, and I get 16x over x squared plus 4 squared. Okay, so now, what are my critical numbers? Critical numbers, what numbers make this 0? Which would be what makes the numerator 0, or makes it does not exist. So I have to look at the denominator. Does that ever equal 0? No, because x squared will never equal negative 4. So I just have one critical number at 0. Now I go to my sign chart. I have 0. This is the sign chart of the first derivative. And I test, say, negative 1, and I test positive 1 into the derivative. And I will get a negative over here and a positive over here. So what does that mean? That means I have a local minimum at 0, because I go from negative to positive. How do you find the y value? You plug it into the original, and you'll get negative 1. So the local minimum at 0 is equal to negative 1, the y value. Last one, just tried to do out some different algebra problems. So the last one, you're going to do the exact same way. Go ahead and find the derivative, guys. So go ahead, pause this, find the derivative, and then you can start it again and see if your derivative hopefully matches. Okay, so the derivative you should get as e to the x over 1, minus e to the x squared when you simplify it. Okay, and now what? Set the numerator equal to 0. When does e to the x equal 0? Never, so that doesn't give you any. And when does the denominator equal 0? So you have 1 minus e to the x equals 0. 1 equals e to the x. So e to the what equals 1 would be 0. So my critical number is 0. Go to my number line, 0. And now I'm going to test -1 and 1 into the derivative. Okay, so if I plug -1 into the derivative, I still get a positive value. E to the -1 is still positive. It's just 1 over e. And if I plug 1 in, I get positive. So even though I have a critical number, I have no local max or min. This could happen. Okay, even though the derivative is 0, this could happen. The easiest, one to think about, because we don't know what that looks like, is x cubed. Think about at 0, the derivative is 0, but that's not a local max or min. It's increasing the entire time, but it flattens out. So the derivative can be 0, but I actually don't have a local max or min. In this problem, what happened? This is actually a value where it does not exist if you look at it. Okay, because this is where the denominator equaled 0. And sometimes what will happen is that's not differentiable, but you still have a local max or min. Okay. Next thing, concavity. So I've quickly talked about it, but I haven't actually done any problems with it. Okay, so a graph is considered concave up if the graph of f lies above all of its tangents on an interval. Just meaning facing up. That's concave up. Okay, why? If you drew a tangent line, all the tangents to that would be below the graph. Okay, so draw little tangent lines, they're all below the graph. Concave down, okay, facing down, so that now if you draw tangents, they all would be above the graph. That's all. Okay, now what does this tell us about anything? If the second derivative is positive on some interval, then the original function is concave up. That's how they're related. Okay, and if the second derivative is negative, then it's concave down. And then here's how it's related to the first derivative. If the first derivative is increasing, then f is concave up. Okay, and if the first derivative is decreasing, then f is concave down. And then we already have done critical points. Now an inflection point is where f changes from being one to the other. Okay, from being concave up to concave down. So changes sign, meaning what? The second derivative must equal 0. Okay, so an inflection point where the original changes. And what the heck would that look like in a graph? That changed. Okay, it's hard to tell exactly where, but I could say about here. This part's concave down, faces down. This part's concave up, faces up. So that at that value, the second derivative would be 0. Okay? All right. And then the second derivative test tells us what? If the first derivative is 0 and the second derivative is positive, then I have this is another way to show local min and local max. Okay, one way is to use the first derivative and show that it changes from positive to negative or negative to positive. Here's another way. If I just said the first derivative is 0, and then I just test the second derivative to see if it's positive or negative, it's another way to show it. Okay? And then this last problem asks us to do a whole bunch of things. Talk about concavity, points of inflection, and local max and min. Okay, use it and then sketch the curve. So kind of putting a couple things together. So the first thing I could do is find the first derivative. So I get 4x cubed minus 12x squared. There's my first derivative. Okay. If I set that to 0 and I factor out 4x squared times x minus 3 and do a sign chart. So I have 0 and I have 3. This is for the first derivative. Okay. And then again, you're going to plug these values in. You're going to plug them into the derivative, because this is the derivative sign chart. You're going to get negative, negative, positive. Okay? So what is this? 0 and 3 are my critical numbers. I know that the function is decreasing from negative infinity to 3. And then it's increasing from 3 to infinity. That's what that just told me. And I know that the derivative is 0 at 0, which means it must flatten out. Now let's do the second derivative to find out more about the function. So I get 12x squared minus 24x. Do the same thing with that. Set it to 0. Factor out a 12x. Left with x minus 2. So now I can come over here and do f double prime. So my inflection points would be 0 and 2. And then again, I would test numbers into the second derivative to see where it's positive or negative. So I'd plug it in here, and I'd get positive, negative, positive. So what's that telling me? That's saying from negative infinity to 0, the original is concave up because this is positive. Between 0 and 2, it's concave down. And from 2 to infinity, it's concave up again. Okay? I'm going to squish the graph in here, just so I can link it all without changing slides, okay? So, we also know just looking at this, that the y-intercept is 0, so we know it's here. Okay, now go to the first derivative. We said it's decreasing from negative infinity to 3. Okay, I know at 3, I have a minimum, because I go from negative to positive. Now, if I actually wanted to find it, I could plug 3 into the original, guys. So if I plug 3 into the original, I'll tell you we get negative 27. So at 3, this is negative 27. And I know I'm decreasing from negative infinity to here. Now, concavity tells me that it's concave up until 0, and then it's concave down from 0 to 2. So I am decreasing yet concave up. It would look like that. Decreasing, coming down, but it's facing up. Now from here to here, from this point to this point, it's decreasing, but now it's concave down. So now it's got to flip, and it's got to go that way. Okay, and then after 3, they're both positive. So I'm increasing concave up, so it would just look like that. So just based on first and second derivative, I just got a sketch of the curve. We'll talk more about concavity and how to draw it, but there's your basic introduction to it.